Hey guys, so let's read the question that we have been given here today. So using the rules of bracket algebra, we have to prove and evaluate the following. So first you have to prove that the trace of xy is equal to the trace of yx. Then we have to prove that xy Hermitian conjugate is equal to the Hermitian conjugate of y times the Hermitian conjugate of x. Then we have to evaluate this expression, exponential of I function of a in bracket form, and a is a Hermitian operator whose eigenvalues are known. And in D we have to evaluate this expression here where psi of a prime x prime is equal to the inner product of x prime a prime. So let's start with the first question where we have to evaluate this. We have to prove this trace of xy is equal to trace of yx. Now since x and y are operators, you know that the diagonal elements, actually forget the diagonal elements to begin with, you know the matrix elements of x. So the matrix elements of x can be written as some a prime x a double prime, and similarly the diagonal elements, since if this is a matrix, these are all the diagonal elements, so the row and column numbers are the same. This is 1, this is 2, this is 3, so these will have all the same values. So a prime and a double prime will be the same here. So here there are two sums over a prime and a double prime since it covers the whole matrix. So the diagonal elements of x can be written as a prime x a prime. So we only need the diagonal elements because the trace is just the sum of the diagonal elements. So let's not write the sum here actually. Yeah, this is how you represent the matrix elements, and this is how you represent the diagonal elements. So we can write the trace of xy, since trace is just the sum of the diagonal elements. We can write the trace of xy is sum over a prime xy a prime, which we can further write as sum over a prime x identity y a prime. Now we know that the identity matrix or the identity operator is expressed as summation of a prime bra a prime ket. We can also change the index if we want, and we can write it like a double prime. So let's put this value over here and let's see what we get. So the trace of xy we are getting as summation of a prime a double prime. Since there are two variables here, now we get a prime x a double prime y a prime. Now if you notice carefully, these two are just scalars, so I can switch them and let's see what we get now. So we get trace of xy a prime a double prime y a prime x a double prime. Now again, this is the identity matrix, so we can write it like trace of xy sum over a double prime yx a double prime. So we get the trace of yx because this here is just the trace of yx. So we have proved the first identity, which was trace of xy is equal to trace of yx. Okay, so let's see what the second question demands. The second question, we have to prove that the Hermitian conjugate of xy is equal to the Hermitian conjugate of y times the Hermitian conjugate of x. So we have to prove that the Hermitian conjugate of xy is equal to the Hermitian conjugate of y times the Hermitian conjugate of x. So suppose there is some state that is say A, and we have x, y acting over it. So think of it like this: if y is acting on a state A, it will give us some other state B, which x will further act on, right? So so this will also eventually give us a state, right? So let's call that state C. So we have the state C is equal to x, y, A, which again we can write as x, B, right? So now if we take the Hermitian conjugate on both sides of this, so what do we get? We get C, and the bra of C, the bra of B, and the Hermitian conjugate of x, right? Now what is the bra of B? Now B, so what is B? B is nothing but y acting on A. So if we take the Hermitian conjugate here both sides, we get the bra of B and the bra of A and the Hermitian conjugate of y acting on the bra of A. So we can put this value over here. So what do we get? We get the bra of C is equal to the bra of A, y Hermitian conjugate, x Hermitian conjugate. So now what is C? C is nothing but x and y acting on A, right? Sorry, this would be the ket. So now if we take the Hermitian conjugate on both sides, what do we get? We get the bra of C equal to the bra of A and the conjugate, Hermitian conjugate of xy acting on A. So from these two equations, we can write that the Hermitian conjugate of xy would be equal to the Hermitian conjugate of y and the Hermitian conjugate of x. I hope this is clear. In the next question, what is the next question? We have been given that the exponential of iota function of A, we have to evaluate in the bracket form. So let's do it. So question number C, we have been given that the exponential of I function of A, and if I reckon correctly, A is some operator whose eigenvalues are known. So it might have many eigenstates. So A is such an operator, like if A acts on some A prime, it will give us some eigenvalue A prime and the state A prime back. And similarly, if there is another A double prime, so it will give us A double prime, that is the eigenvalue, and the state A double prime. So we can write A like summations of A, some eigenvalue, and A prime. We can express A like this. So let's see what is the eigenvalue of A square. So A square of A prime is just nothing but A acting on A of A prime, right? So what is this? This is just A prime, the state A prime. So we get A of A prime, which we'll get A prime square, A prime. So this results in this value. So we can write that A square of A prime is just A prime square, A prime, right? So how do we express the operator a square? So a square can be represented like the summation of a prime, a prime, a prime bra, a prime ket, sorry, a prime ket, a prime bra, times there would be another one here, that is a double prime, a double prime, a double primes ket, a double primes bra. Let's simplify it a bit more. So what do we get? We get two sums, a prime and a double prime, a prime, a double prime, and we have a prime, the inner product of a prime and a double prime, and a double prime. So this here is since these are orthonormal, I'll assume them to be orthonormal. Is it given if they are orthonormal? No. Since they are eigenkets and eigenbras, I can assume them to be orthonormal, I think. So I'll consider them as a Dirac delta. So this will only give us 1 if a prime is equal to a double prime, and will give us 0 if a prime is not equal to a double prime. So we can write it as just one sum, and since all the rest these values will be 0, we'll just consider this case. So a square we can write it as a prime square, the ket of a prime and the bra of a prime. So similarly we can say that the operator an, oopsie, I changed the pen, yeah, so the operator a to the power n would just give us, would look something like a prime of n, a prime, right? So what would be the function of a look like? What would the operator, we have this operator, right? So how would the operator f of a look like? So we know that a is if a acts on a eigenstate a prime, we get a prime and the ket of a prime. So the function of a should act similarly, like if a function of a acts on a prime, we should get some eigenvalue which is a function of a prime, the initial this eigenvalue, and the ket a prime. So then we can say that the operator f of a should look like f of a prime, the ket of a prime and the bra of a prime. It should look something like this. So how would the operator function of a to the power n look like? So if function of a to the power n acts on some state a prime, we'll get some function of a prime to the power n a prime. This is how it should look like, right? So how do we prove it? Does it, like, how do we know if it's correct? So if we have a function of a double prime, so we can write it as some a prime function of a prime and a prime a double prime. We know this is the Kronecker delta function. Oh, I apologize if I called it the Dirac delta function here. It's the Kronecker delta function. I'm so sorry about it. And so here we get the Kronecker delta function here. So this will only give us a value, like it will become 0 if a prime is not equal to a double prime, and so it will only give us a value if a prime is equal to a double prime. So the function of a acting on the state a double prime will give us function of a double prime acting on state a double prime. So we know that since this works, our formulation works, so we know that this is also correct, and this that we have formulated previously, the operator f of a, is also correct since our formulation works. So let's calculate the exponential of I f of a. So this is also an operator, right? So this is an operator. So what do we get if we act it on a state? If we operate it on a state, say a prime, there's no space here, let me write it below. So exponential of IFA a prime, if we acted on this state, what do we get? We get the exponential function and IFA n factorial a prime, the state a prime. So this is the operator here, this operator is the one that is acting on the state a prime. So we have to check what do we get. So we get exponential IFA a prime equals, so if this here acts on this operator, just consider this part, wait, so f of a n, if just acts on a prime, so we'll get f of a prime n a prime, right? We just proved it above. So this will just fetch us, this will just fetch us that exponential of n goes to 0 to infinity and another sum a prime I of f of a prime n by n factorial a prime. So how would this operator look like then? So exponential of IFA, this operator would look like a prime exponential of IF a prime, since this is the eigenvalue and this is just a number, not an operator, a prime ket and a prime bra. So let me write it a bit more clearly since it's pretty cumbersome here. So the final answer that we get, it's like a prime exponential of if prime a prime get a prime bra. So this here is how this operator would look like. So let's do the fourth and the last question. D, what did it say? Let's check. So we have been given this expression and we have to evaluate it, this expression where we have that psi of a prime x prime is equal to x prime, the inner product of x prime a prime. So let's see, let's write the expression that we have been given first. A prime psi star a prime x prime psi a prime x double prime. You have to evaluate this expression and we have been given that psi of a prime x prime is equal to this, it was x prime a prime, right? So let's just put these, so a prime x double prime would be similar, it would be x double prime a prime. So let's just put these values here. So we'll get a prime x prime a prime star and x double prime a prime, right? Which we can write as a prime x prime x double prime a prime, right? So now since these two are just scalars, I can rearrange them as x double prime a prime a prime x prime. So you recognize this, don't you? This is the identity matrix again. So we just have this here, that is x double prime x prime, which is just again the Kronecker delta function of x prime x prime x double prime x prime. So this is what the expression is basically. It's just a Kronecker delta of x double prime x prime, and it will be 0 for x double prime when x double prime is not equal to x prime, and 1 when x double prime is equal to x prime. That was all of this question. Yeah, thank you for watching.